Our universe, the galaxies, the solar system, our home planet Earth, land, sea, air, and life itself. Where did it all come from? If you look into space from our planet, you will see a vast cosmos streaming of billions of stars and galaxies. But then on the clock 13 billion years, and our universe was so small it could fit inside the palm of your hand. Describing how the universe evolved from that small spot up to now and predicting what will happen in the future is a very difficult problem. We need to modify our models every time so that it fits the data very well. The perfect fluid cosmological models are built on the dynamics governed by Einstein's theory of general relativity, with the cosmological principle valid at large cosmic scales and the assumption of cosmic composition as idealized perfect fluid. In other words, all the components of the matter and energy in the universe are considered as perfect fluid with zero viscosity. The most idealized standard description for current cosmology is the lambda CDM model, which obtains a constant dark energy term, the famous cosmological constant, that corresponds to 70% of the space and fits the observational dataset very well. We try to improve the lambda CDM model by considering the viscosity of the fluid. This will change the energy momentum tensor. So, if we consider the case of a homogeneous anisotropic universe and focus on the bulk viscosity while neglecting the dissipation and the shear viscosity, the full expression for the momentum energy tensor that contains the pressure of the bulk viscosity reads as equation 1, where psi is the bulk viscosity parameter. We are going to use two types of temperature-dependent viscosity. The first being described by Chapman-Inscoed equation, and the second by Sutherland's formula. Both equations can be written in the form of equation 3, where alpha is a constant that has a value of half and 3 divided by 2 for the case of Chapman-Inscoed and Sutherland's types of viscosity respectively. Substituting this viscosity formula in the pressure equation, Einstein field equations now reads as equation 4 and 5, where rho lambda is the energy density of the dark energy, rho m is the energy density of the pressureless matter, and c is the speed of light. Manipulating Einstein field equations, we managed to get an equation that relates the Hubble parameter to the redshift. This relationship is given by equation 6, where the power index above is plus half for Sutherland viscosity and minus a half for Chapman relationship. Our proposed model will be given the name lambda CDM V, where V stands for viscosity. Furthermore, a letter A or B will be added to indicate a value of alpha equals to half or 3 divided by 2 respectively. To find the best fit values for Hubble parameter and for omega matter and omega dark energy, we use the MCMC algorithm. For lambda CDM V A, we got the following results, while for lambda CDM V B, we got these results. One thing to consider in mind is that the evolution of the viscosity is related to the expansion scale factor. This means that the viscosity will be gradually reduced by the ongoing expansion. This will provide us with a physical acceptable transition mechanism of the fluid from being imperfect to a perfect fluid during the cosmic evolution. From the above results, one can say that lambda CDMV, the viscosity model, can be a replacement for lambda CDM, since it is more general because it includes the viscosity and it also fits the observations to a very good approximation.